You've waited for it. Here it comes, the definition of convergence and continuity. After this video, you will know how to define convergence of a sequence in any set, in any topological space. So let's get started. We start with a topological space X and a sequence Xn of elements of X. We say that Xn converges to the limit L if, for any neighborhood of L, there exists a rank after which Xn is in V. So let me say this again, it's important. That's the definition of convergence in a topological space. For any neighborhood V of L, there exists a rank n for which, after n, Xn will be in V. There is something strange, though, which is that Xn may converge towards several elements, and that's very unusual. I'm sure you're very surprised by this result. However, if you have additional property on the topology, you can guarantee that there is only one limit. And the property that you need to have is what we call the Hausdorff space. And in the PDF supplement, you will see that there are quite a few properties that you can add to topological spaces that will provide additional results. I'm just going to talk about Hausdorff spaces here for just one sec. Basically, a space X is T2, or is a Hausdorff space, that's the definition, or is separated, if when you choose 2 points, any 2 points in X, you can find 2 open disjoint sets, each containing a point. If this is the case, then the space is a Hausdorff space. And in this case, the limit of the sequence will be only one. There's only one limit possible in a Hausdorff space. So back to the definition of convergence. As you can see, this definition will work for any topological space. And if you choose a different topology, you will have a different convergence. So for each topology, you will have a different convergence. If you equip your set with 2 different topologies, then you might have 2 different ways to converge. As a matter of fact, in one topology you might converge, while in the other topology, maybe you don't converge. If the topology is stronger, larger, or finer, what happens? You're going to have more open sets, right? So you're going to have more neighborhoods. Therefore, to satisfy that for all neighborhoods of L, blah, 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 you're going to have, it's going to be more difficult. It's going to take more effort to converge. So the situation is that if the topology is stronger, then it will be harder for Xn to converge. And if you actually have the discrete topology, meaning that everybody is an open set, then only sequences that become constant after a certain rank will converge. Let me now define continuous mappings, or continuous functions. You choose 2 topological spaces, X and Y. The mapping F will be continuous if the inverse image of an open set is an open set. That's the definition of a continuous mapping from X to Y. You will see in the PDF complements that you can also define the continuity around the point. And then you will say that the function is continuous if you have the continuity for every point. So you can either start with the local continuity and derive the global continuity, or start immediately with the global continuity, saying that a continuous function is one that will map, an inverse map, a open set to an open set. Now, if the topology on X is finer, larger, stronger, meaning you have more open sets than in another topology, then it will be easier to be continuous. Since you have more open sets, the inverse image of an open set will be in X, and that will be easier to be continuous because you will have more open sets to choose from. So if you have a topology with more open sets, in other words, if you have a finer topology, then it will be easier for a function to be continuous. And by the way, if X is equipped with a discrete topology, all of the mappings will be continuous, because you can take the inverse image of anything. That will be obviously a subset of X, and that will be an open set. You can see that these two definitions, convergence of a sequence and continuity, work really well together. Let me actually give a proposition here. If you choose X and Y, two topological spaces, and you choose a continuous function, f, between X and Y, and you choose a sequence xn in X, converging to L, and you define yn to be the image of xn by f, then yn will converge to f of L in Y. And I'm going to prove it. I start with any neighborhood of f of L. There exists an open set U such that f of L is in U and such that U is included in W. That's the very definition of a neighborhood. But we know that f is continuous, right? So the inverse image of U by f will be open. Now, we also know that f of L is an element of U. So we have L in f minus 1, the inverse image of f of U. But we also have that inverse image of U is included in the inverse image of W, because you have U included in W. So if you look at all of this, basically at these three things here, you can derive that the inverse image of W is a neighborhood of L. All right, so here's what we did. We started with W, a neighborhood of f of L, and we have V, which is the inverse image of W, which is a neighborhood of L. Now, let me go back to the definition of the convergence. We know that xn converges to L, so we know that for any neighborhood of the limit L, there exists a rank n, capital N, such that after this rank, xn is in V. And if it's true for any neighborhood, I can choose V equals f inverse of W. So I do this, and it means there exists a rank n, after which xn is in f inverse of W. Wait a minute. This means that yn will be in W. Therefore, for any W, and again, I started with any W possible, which is in the neighborhood of f of L. Then for any of these W in the neighborhood of f of L, there exists a rank such that after this rank, yn is in W. That is the exact definition of the convergence of yn to f of L. That ends the proof.